Hello everyone. Today we will see lab program 7 of design and analysis of algorithms laboratory. The aim of the program here is to, from a given vertex, we now need to find the shortest path to all other vertices in a given weighted connected graph using DIJKSTRA'S algorithm. So we'll have to now implement the DIJKSTRA'S algorithm, which now finds the shortest paths from a given vertex to all other vertices. And we need to implement the same program in Java. So in order to look into the program, we'll have to first look into what is DIJKSTRA'S algorithm, how it works. So the DIJKSTRA'S algorithm is a one. Given a graph and a source vertex in the graph, it will find shortest path from source vertex to all other vertices. This problem or this DIJKSTRA'S algorithm is also sometimes known as single source shortest path problem. And this problem of single source shortest path is now solved by using a design approach, algorithm design approach, that is greedy method. So we can now see the same in the following example. So given a graph, so this is a graph, and we can see that this graph has now 6 vertices, A, B, C, D, E, and F, 6 vertices, and it is a weighted graph. That means to say all the edges do have a weight associated with them. So I consider now the source vertex is A. So I consider A as my source vertex. So my aim for this particular DIJKSTRA'S algorithm problem is, given the source vertex, I'll have to find the shortest paths from source to all other vertices. That means to say, I'll have to find the shortest path from A to B, A to C, then A to D, then A to E, then A to F. So we need to now calculate the shortest path from node, which are as now follows. From node A to node B, the shortest path you can now see is of distance 10. So I can reach A to B with a distance of 10, which is now the shortest one. So A to B, right? So the path is now A to B, which is of distance 10. Similarly, A to C. So I can also reach A to C with a path of A to C, whose distance is equal to 15. Similarly, we have D. So we can now see I can reach D from A through the path which goes like this, A to B, then B to D. So which is of distance 22. 10 plus 12 is 22. Next, the next vertex is E. You can now find there are 2 paths from A to E. One path is A, B, D, E. The other path is A, B, F, E. So A, B, D, E, if I consider the path, we can find the distance is 24. 10 plus 12, 22 plus 2 is 24. But if I take the path from A to B, B to F, then F to E, you can see the distance is 30. 10 plus 15 plus 5, which is equal to 30. So I am interested with shortest path. So I will now select the path A to B, B to D, D to E, which distance is now 24. Next vertex, the last vertex is F. So F also you can see there are 2 paths with respect to A to F. So one path is A to B, B to F, whose length is 25. And the other path is A to B, B to D, D to F, whose length is 10 plus 12, 22 plus 1, 23. So I am interested with the shortest path. So the shortest path from A to F is of a distance 23. Right? So this is what we are now supposed to find using the DIJKSTRA'S algorithm. So given a graph and a source vertex, we need to find the shortest path distance from the source to all other vertices. Now how exactly the DIJKSTRA'S algorithm works? The DIJKSTRA'S algorithm works in this following way, in the following steps. Any vertex which has been selected as a source vertex. So I can select any vertex as a source vertex. And we all know that the distance between a source vertex to itself is 0. So because why I tell that distance between a source vertex to itself is 0, because I am bothered in finding a path from source to all other vertices, and therefore the distance between a source vertex to itself. So I am not considering the path from source to source. No, I'm considering source to all other vertices. So therefore it is 0. So initially, we now assume with respect to all other vertices, right? They are at the distance of infinity from the source. So what do we do? So initially we tell the distance from source to source is 0. Then the distance from source to all other vertices will be assumed to be as infinity. So why do I assume it to be as infinity? Stating that the distance between source to all other vertices is right now not available. So it's infinity. Next step in the algorithm is I should now maintain one array called as a D. So what is this D? So as I said, distance of source to source is 0. Distance of source to other vertices is infinity. Right? So I should store it somewhere. So I use an array so called as a D, where I initialize D of source equals to 0. So what is this D of source equals to 0? Distance of source to itself, right? Distance of source to itself. So D of source indicates distance of source to itself is equal to 0. And for other vertices, it is infinity. So it means to so here we now need to initialize the array D. Okay. So the D array is of size n. So what is n here? N represents the number of vertices in a given graph. So for int I equals to 0, I less than equal to n I plus plus. So I initialize all the entries of di equals to 999. The reason because the distance from source to all other vertices is 999. So I here refers to the destination vertex, because source is always common. Source to I. So you remember here that D of I. So D of I, when I write, it is nothing but the distance of source vertex to I. So this D of I represents the distance of source to I. Remembering that. So we also now have one more array, so called as visited array. So there's an array again, a visited array which is of size again n, right? So visited array. So this visited array is an array which is basically used to maintain which vertices are visited. So in this concept of visited array, if visited of I is equal to 0, means that vertex is not visited. Vertex is not visited. And if it is equal to 1, it means that vertex is visited. So we have this concept similar to Prim's algorithm. So wherein we select the edges in Prim's, as you all know, such that the source vertex of the edge is visited and the destination vertex of the edge is not visited. The same concept we will be using here. So to maintain that concepts of visited and not visited, right? So we use an array so called as visited array. So where the entry of visited of I equals to 0 means that the vertex is not visited, and 1 means that the vertex is visited. So initially I make all the vertices are not yet visited. So they're not yet visited, and the distance of all the vertices from source to I, where I ranges from 1 to n, it is initialized to 999. And along with that, we also know that distance of source to itself is 0. So I should now take D of source. So D of source is now equal to 0. So D of I initialize it to 999. And after the D of source is equal to 0. The next here is with respect to the next step we have is to find, next is to find the direct neighboring vertex. So direct neighboring vertex of the source vertex. Find out which is the direct neighboring vertex, means to say from the source vertex, which is the adjacent vertices to source. And how do you select that direct neighboring vertex, which is at a minimum distance? So from a source, it should be at a minimum distance. So direct neighboring vertex refers to direct edge from the source vertex. Let us assume for some source vertex, we have two neighboring unvisited vertices, remember. So the vertices which you consider should be an unvisited one, right? So directly you will have to now find from source to the adjacent vertices to source which are unvisited, right? So for some source vertex, as an example I am taking, if there are two neighboring unvisited vertices, A and B, which are at a distance 2 and 4, so which one should you select out of this? So I should now select the vertex which is having minimum distance. So it is 2, right? So 2 corresponds to which vertex here? The 2 corresponds to now vertex A, right? So then the minimum distance is now A vertex in this case, because the distance of A is 2 and that is the minimum one. So I'll have to now call one method so called as find minimum distance, wherein what is this find minimum distance doing? It finds the neighboring unvisited vertex which has the minimum distance from the source vertex. So how does it find? Find minimum distance D. So why I used the array D here is because D array holds the distance from every vertex, right? It holds the distance of source to every vertex, right? And visited, why I need? Because I'll have to find out the vertex which has got the minimum distance in D array, which is not yet visited. So I should use visited array. So out of these two arrays, using these two arrays, I'll now find a vertex, right, which is now having the minimum distance, right? Once you find this minimum vertex distance, we mark this vertex as a visited. So mark this as a visited. And after marking it as visited, calculate the distance of each direct neighboring unvisited vertex of U. So now what I should do? After making it visited, calculate the distance of each neighboring unvisited vertex of which one? U. So again, the same concept I should repeat for U with some formulas. So how do you mark the vertex U as visited? Visited of U equals to 1. Because U is now marked as visited. What is U? U is a minimum distance vertex, which is still not visited. So mark it as visited. Next step is now to find out the distance of direct neighboring unvisited vertex of U. When I tell direct, means to say it is the vertex which are adjacent to U. That's what I mean. So I should calculate now the distance of the vertex which are adjacent to the vertex U. And whichever vertex is now adjacent should be unvisited. Let us see how do we calculate. So it is something like this. If the sum of the distance of minimum vertex, so which is your minimum vertex? U. So you know that if D of U plus cost of the edge to the neighboring unvisited vertex, A of U comma V. So what is A? A is your adjacency matrix which holds the representation of the graph or which holds the weight. Yes. So D of U. So D of U is what? Distance with respect to the minimum vertex plus AUV is what? Weight of the edge from U to V. Where U is visited, V is still not visited. And U and V are adjacent. If I summate this, Is this less than d of? So here we now need to find out the sum of the minimum vertex distance d of u plus a of uv, whether it is less than dv. So what is this formula telling you? Very simple. Du gives what? The distance from source to u, plus AUV gives what? The weight of the edge reaching from U to V. So when I summate these two, I will get a new distance of reaching from source to V. Very simple as it is. Try to understand. So here du gives me what? The distance from source to U, plus AUV gives the weight of the edge reaching from U to V. This is nothing but the new distance of V. Is this value less than the old distance which is already stored in dV? So what is dV? You all know that. dV is nothing but the distance from source to V. If at all the new distance is less than dV, in that case, update dV equals to du plus AUV. Right? So this should happen for every vertex V which is not visited. So visited of I, you can now see here, visited of V, sorry, should be equal to 0, and du plus AUV is less than dV. Then update dV is equal to du plus AUV. And this process, whatever I just said previous to this, that is computing the distance of dV where V is visited and such that U and V, there is an edge. The process of identifying the vertex U as well as the vertex V, finding the distance. The process of these all should be repeated until we visit all the vertices of a given graph. So keeping this into mind, so let us now see one small example for the same. So the example, before we go for the example, we'll see how exactly the graph has to be represented. So this is a graph, as you all know, we use a weight matrix or a cost adjacency matrix. Since I cannot use in my computer program the numbering as for 2D array as the index numbering as ABCD, I have mapped it to the numbers 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 respectively. You can now see A to B. There is a edge from 1 to 2 whose cost is 10. Similarly, A to C. There is a edge from A to C. That means 1 to 3 whose cost is 15. So if there is a edge, write its respective weight. There is no edge, write 999. For no self loops, you should write 0. So keeping this in mind, which I've already covered in Prim's algorithm concept. So let us now iterate over the graph. So I should get the answers which I just told you. That is the shortest path distance from A to B is 10. Shortest path distance from A to C is 22. A to D, sorry, 22. A to C is 15. So similar answers I have to now get by tracing the algorithm. So for tracing the algorithm, first I'll maintain the visited array whose size is 6. Similarly, the D array whose size is 6. And similarly, I have the adjacency matrix here. So I have a table which is similar to the steps what I told you. The iteration numbers I give. So I'll have to repeat this till I visit all the vertices. So how many vertices I have? 6 vertices. So I'll have iteration 6. 6 times I'll have to do it. The first step, what should I do? Find U such that U is not visited. That is visited of U equals to 0 and du is minimum. Okay. After selecting the U, mark it as visited. That's what I said in the first step, right? Visited of U equals to 1. The next step is what? Find V which is adjacent to U, and V should not be visited. Yes. Next, what should I do? Update dV. So dV is nothing but what? Minimum of dV, comma, du plus AUV. Right? dV is what? Distance from source to V, which is already recorded. du gives me what? Source to u, the distance, plus the weight of the edge reaching v via u to v. Right? So let us now repeat the process. The first iteration. So in the initially, you can now see the first row here, right? You can now see all the vertices are not visited. So visited of I equals to 0. Initialization has been done here. And you can see the D array. So I told you the distance from source to source is now 0. So I assume that by default my source vertex is 1 here, right? If even in your exams, if they don't give you the default vertex is always your first vertex, right? So anyways, I have given the word source vertex as 1. The source to source is 0. The rest all is 999, right? The distance from source to all other vertices is 2, 3, 4, 5, 6, 999. Now the first step here is find the u, okay, which is not visited. So I want which is not visited. Now you can see initially none of the vertex are visited, right? So I should find the minimum such that it is not visited. So you can now see in D, which is the minimum value. So which is the minimum value in D. You can see 0 is now the minimum value, which corresponds to which vertex or which value of u? It is 1. So, and you know that 1 is still not visited. Yes, it is still not visited. So now, what should I do with respect to this since it is still not visited? So I'll take u equals to 1. And what is d of 1? You can see d of 1 equals to 0. And visited of 1 now is marked as 1. So this row, the second row will happen once the iteration 1 is completed. So in first updation in your visited array, you can see in visited array, visited of 1 is marked as 1. So I've used red color here. So it is marked as 1. Next, which are the vertices V now which are adjacent to U which are still not visited? So you can now see U is 1. So go to your adjacency matrix. U is 1. Here it is. And which are the vertices adjacent to U which are not still visited? So you can see which are the vertices adjacent to 1 because U is 1, right? The vertices which are adjacent to U are now 2 and 3 whose weights are 10 and 15, right? You have marked with the red fonts color 10 and 15 here. 2 and 3, you can see 2 and 3 are still not visited. So I should consider both, right? So 2 and 3, they are still not visited. Consider both. Next, find out, update the value of dv, right? So d2 and d3 is equal to minimum of dv. So what is dv? You have observed that in D array, what is dv? dv, you can see it is 999. Don't go for the second row, the first row only there, okay? After updation, we will update D array here. So D2 is still 999. That means to say, I have recorded that I cannot reach from source to 2. Right? Now I'll see whether I can reach to via U. Okay? DU. DU is what here? D1. D1 is now what here? You can see D1 is 0. Because U is 1, D1 is 0. 0 plus A of UV. So A of 1 comma 2, that is what? 10. So 0 plus 10. 999 comma 10. So which is the minimum here? 10. So D2 now becomes 10. So D2 gets updated as 10. The reason because I am now able to reach 2 from 1. 1 to 2. I am now able to reach. Right? Next, similarly, update for D3. D3 is equal to minimum of, what is the value of D3? Here you can observe value of D3 is 999, comma, D of U. D of U is what? 0. Put 0 plus, and it is 15 here. So you can observe A13 is 15. So minimum is 15. So I'll update D2 and D3, which is now 10 and 15. Remember this row to be updated, the iteration number what I have given once I complete the iteration. Now, next step is step 2. Now again I should again find DU such that it is not visited and is minimum. Okay. Now you can observe in the first iteration now, which is visited? Only vertex 1 is visited. The rest are all not visited. So I should now find out in D matrix, except this, except the D1, I should find out which is that which has got minimum value, right? Out of 2, 3, 4, 5, 6. You can see out of 2, 3, 4, 5, 6, which is that which is having the minimum value? That is your DU and U, right? So which is the minimum value here? You can now see D2 10 is the minimum value and U is what? 2. So U corresponds to the vertex and DU corresponds to the distance. So in the array, U is your index, DU is your value. Remember, the minimum is 10 and the U is 2. So U equals to 2, D2 equals to now 10 and make it visited. So I marked it as visited here. Can you see in the second iteration row, right? 1 is already visited previously, 2 is also visited now. Now, which are the vertices adjacent to 2 which is still not visited? So which are the vertices adjacent to 2? You have 4 and 6. And you can see here 4 and 6 still they are not visited. Reason because the entries are still 0. So 0 means not visited, 1 means visited. Similarly, we'll now calculate D4 and D6. So you can see 999, minimum of 999, D2 is 10, 10 plus 12 is minimum is 22. Similarly, D6 gets updated as 25. So you can now see the changes here. You can now see the changes here. You can now see the changes with respect to D4. See, D4 earlier it was 999, now becomes 22. And D6 was also 999, now becomes 25. So what does it mean now? I am not able to reach D4 with a distance of 22 via the vertex 2, right? Via the vertex 2. And you can remember with the previous iteration, how did I reach vertex 2? Via 1. So 1 to 2, 2 to 4 I have reached. So the concept is moving stepwise. First you will find the shortest. From there you will find out which are all the vertex can be reached in the shortest distance. From source to some other vertices using shortest. From that source, from that vertex to all other vertices. So it is like an intermediate process which goes there. Next, the third iteration, again it is, you can see, which are the now vertices visited. 1 and 2 are visited, isn't it? So in my D array, now I cannot consider 1 and 2 because they are already visited. So I should now consider the value entries in D3, D4, D5 and D6. Out of all these 4 entries, which is the minimum? The minimum is now 15 corresponding to the U value, that is 3. So U equals to 3. Remember, U is the vertex, DU is the value. So in your array, DU is the value, U is the index. So 3, D3 is 15. And make visited as 1, the very important, right? Because if you don't make this as 1, then the rest goes wrong. Because we are bothered about visited and unvisited concept. So which are the vertices adjacent to U? That is equal to 3. You can now see only 1, 10 corresponding to the vertex 5. So 5 is still not visited. So again calculate D5. D5 is equal to minimum of 999 comma 15 plus 10, which is equal to 25. You can now see here in your third iteration, D5 which was 999 now becomes 25. So it's updating. You can see it is the distance are getting updated, right? Similarly, I'll have to now go for the next iterations, right? The fourth iteration, fifth and sixth. So I told you number of vertices, that many iterations will be there. So similarly with respect to fourth iteration. So for fourth iterations, I should consider the third iteration input, right? So you cannot take fourth iteration, first consider the previous one, isn't it? So you can observe that all the 1, 2, 3 vertices are visited. Non-visiteds are what? Right? 4, 5, 6. Now let us see the third iteration entry of D. 4, 5, 6. 4, 5, 6, out of which is the minimum there. The minimum here is the 22 value, which is corresponding to the vertex 4. 4 is the minimum value there, right? So u equals to 4, d4 is equal to 22 and make 4 as visited. So update the fourth iteration visited values, right? Now you can see 4, which are the vertices adjacent, 5 and 6, right? 5 and 6, and they are still not visited. Very important. Find u such that they are not visited. That's very important. You cannot select. Suppose in this example, if 5 was visited, you cannot select 2. Right? The fifth vertex cannot be selected. Right now it is not visited. No problem. 5, 6. Again update 5 and 6. You can observe here d5 is equal to minimum of 25. Why? Because earlier d5 in third iteration updated to 25. So you should write that. So d5 is 25, comma 22 plus 2. You can now say earlier I stated that I could reach 5 with the weight or the distance 25. Now I can tell it is reaching with the distance 24. So it is getting updated because shortest path I'll have to find, isn't it? And even d6 you can see here. d6 earlier it was 25 and it now gets updated as what? Updated as 23 because that's the shortest there. So I'm getting updated. You can now find here that d5 earlier was 25, gets updated to 24. d6 earlier was 25, which gets updated now to 23. So you can now see 5 and 6 are reached in a shorter way via the vertex 4. So how vertex 4 is reached? Right? You should go back to the next table. So vertex 4 got reached via which path? Right? So the next table will give you that entry there. Next iteration similarly, finding out which are the vertices not visited having the minimum du value. So again you can see 1, 2, 3, 4 is visited. Left out is only 5 and 6. Right? So 5 and 6 here not visited. Look at it. Which is the minimum value here you can see. Right? The minimum value here is now with respect to 23, the vertex is 6. So u is equal to 6, d6 is equal to 23. Mark it as visited. Which is the vertex adjacent to 6? The vertex adjacent to 6 is only 5 with respect to 5 vertex. You can see 5 vertex is still not visited at distance 0. Right? Now, start calculating d of 5. So d of 5. Earlier it is 24, it remains as 24 because this is slightly larger, 28 I'll get. If I take a path from via 6, I'll get 28, which is larger than 24. So I'll not update, retain it as it is. Okay, next iteration, which is left out one. The left out one is only your fifth vertex. So fifth minimum value is 24, which has been considered. Right? So considered. So fifth vertex, is there any vertex adjacent to fifth vertex? Can you just see here? There is no vertex adjacent to now the fifth vertex. So nil and no updations. After sixth iteration, the values remain the same. Can you see? 0, 0, 10, 10, 15, 22, 24 and 23. And marking 5 as visited. You can now see all the vertices are visited. So I should now stop the iteration. So I'm done with the iteration process. Now, how do I get the distance? Now I'll have to use the D array. The final D array entries I should consider 0, 10, 15, 22, 24 and 23. 0, 10, 15, 22, 24 and 23. So as I told, what does this D1 give me? D1 gives the shortest path distance from 1 to 1. Right? That means source to 1. Similarly, D2, what does it give? It gives the shortest path distance from source to 2. Similarly, D3, shortest path distance from source to 3. Similarly, 4, distance from source to 4. Right? So your source vertex is now 1. So I will not consider the distance from 1 to 1, which is 0. Not required. I am bothered about distance of shortest path distance from source to all other vertices. The shortest path distance from 1 to 2 is D2, which is the distance is 10. 1 to 3, the distance is 15. 1 to 4, the distance is 22. 1 to 5, the distance is 24. And 1 to 6, the distance is 23, which is the same which I told you in the earlier slide with respect to the example. Same values you will get. So shortest path distance from source to all other vertices will be stored in your final D array. You have to extract it. So you must know the D array gives the shortest path distance from source to all other vertices. Remember, in any program related to graph, the indices of an array represents the vertex. Any program you take. So 2 if I write, it is second vertex, 3 third vertex. But here the D array indicates now the shortest path distance from source to 2 is 10. Right? Source to 3 is 15. So this is how you can get. So your source vertex can be anything. So it is left to the programmer what can be the source vertex there. So coming to the program here, so you can just see the first I will have to read the matrix. So I have a class called as a register. So inside this class I have 3 methods: read, minimum distance, and the problem of finding shortest path with the main method. So 3 methods along with the main method. So I declare n comma source, which is number of vertices and the source vertex. A is your cost adjacency matrix. So I've already told you this in your prims. So reading the cost adjacency matrix, ask the user to enter the number of nodes, ask the user also to enter the cost adjacency matrix. So I am starting the vertex numbers from 1. So the for loop should iterate over from 1 to n, 1 to less than or equal to n, which will be stored in the array A. And also ask the user to enter the source vertex. So it will be stored in SRCS. And the scanner class object is now being closed. Now, the other method which we'll now see here is int find minimum distance. So as I told you, find minimum distance is a 1 which finds the minimum distance vertex from D, which is still not visited. So there are 2 parameters, D array and the visited parameter. So initially, I assign minimum distance equals to 999 and minimum distance vertex is equal to -1. So some initial values have been initialized. I will iterate over the D array to find the minimum distance value. So for I equals to 1, I less than or equal to ni plus plus. So to find the minimum, there are 2 constants. One is the vertex should not be visited. Yes, the vertex which you consider the minimum value, it should not be visited, and the distance should be the minimum one. So I have 2 constraints. How do I impose those 2 constraints? If visited of I double equals to 0. So we know that there's an array called as visited whose entries are 0 means the ith vertex is not visited. If the entry is 1 means the ith vertex is visited. Right? So I want the ith vertex not to be visited. So visited of I equals to 0 and D of I is less than min distance. Min distance is initialized to 999. So iterating over this, I will get the minimum distance value. How do I update if D of I is less than min distance? Min distance is equal to D of I. Update the vertex also. Minimum distance vertex equals to I. Yes. So I'll iterate for the entire array of D, find out which is the minimum distance vertex, and I'll return that, which is the return type is now int. See, if I get minimum distance vertex, right, I can get the minimum value. So D of that particular vertex is the minimum distance value. So I'm just returning only the vertex value, not returning the value. Okay. I'm just returning the distance, minimum distance vertex, which is that vertex which is giving me the minimum distance vertex. It's been returned, which gives me the minimum distance via which I can access the minimum distance. Right? So my return value is just the vertex wherein using that vertex, I can get the minimum distance. Now the other method we have, that is the DIJKSTRA'S method, which will now compute the shortest path for me. So I have created two arrays, as I told. I need visited array and D array, which are of size 10. So next thing is initialization. So we make first all the vertices not visited. So visited of I equals to 0 for every I ranging from 1 to n. And D of I is equal to 999. Why I just told you? The distance of all the vertices from source is initialized to infinity. So in program, we cannot write infinity. We cannot type. So I initialize it to 999. And I also told you that distance from source to source is always 0. So first let me initialize the D array and visited array. After initialization, just initialize D of source equals to 0. Right? The distance of source to source is 0. You have to initialize this. If you don't do this, again, you will not get the solution to the problem. So stepwise you should do, right? Next, as I told you, I should repeat certain steps till all the vertices are visited, right? So you can now see for int I equals to 1, I less than equal to n, I plus plus. So this is comment with respect to this. The distance of source vertex to itself is 0. Comment for this. So I'll have to iterate over all the vertices. Some steps I have to do till I visit all the vertices. So I have given I is equal to 1, I less than equal to n, where n is the number of vertices. So what should I do? I should find a neighboring unvisited vertex having the minimum distance from the source vertex for the first time. Because you all know that D of source is 0. That is minimum. For the first time, your U will be the source vertex itself. If you can traverse back, you can see in the table, for the first time, U is your source vertex only. Right? That's what the comment I have given here. Find a neighboring unvisited vertex having the minimum distance from the source vertex for the first time. Because U will be your only source vertex. Right? Otherwise, you will have to find the neighboring unvisited vertex having the minimum distance. Okay, from the source vertex. Right? For the first time, U will be the source vertex for the first time. Otherwise, U will be some other vertex. Let us not bother which vertex is this. Right? And the distance array will be updated with the neighboring vertex distance of source vertex. Isn't it? So I'll have to update the distance array such that with the neighboring vertex distance of the source vertex. Right? How do we now update this? First, let us now find the minimum vertex or the minimum distance vertex by calling the method find minimum distance. So find minimum distance, if I call, I'll get the vertex which has got the minimum distance which is still not visited. That is stored in U. So you all know that for the first time, U will be your source only. For the next iterations, U's are different. Right? Visited, after you get U, mark the U as visited. So visited of U equals to 1. Okay? For the next iterations, U is your row, acting as your row, V is the column. So for the next step, what I should now do? I should now update the distance array such that with respect to U, which are all the neighboring vertices, right? So I'll have to now update it. Okay. So update the neighboring vertex distance of the source vertex. Initially I'm talking. So update the neighboring vertex distance, right, of the source vertex. Right. So neighboring vertex distance I should be updated. And you remember that the neighboring vertex distance or the neighboring vertex should also be not visited. So which are all the neighboring vertex? How do I identify? Again, I'll have to traverse, right? So for V equals to 1, V less than equal to n, V plus plus. So we have V acting as our neighboring vertex. And you all know that the visited of V should be equals to 0 because the neighboring vertex should not be visited and D of U plus AUV should be less than D of V. That means distance of source to U plus the length of the edge UV. If I summate, it should be less than the already available distance from source to V. These two conditions are now being satisfied. Update dV. dV is equal to what? du plus AUV. Okay. This is the end of the if, and then the for. This is the end of this for loop. Wherein all the steps, finding minimum distance, updating U as visited, finding all the neighbor vertices, and updating all the neighbor vertex distance. So your neighbor vertex should be unvisited, right? And update the distance if this condition satisfies, right? So we will repeat the steps. Once the steps are being done, updating the distance array, right? So I'll have to print the values of the distance. So how do I print the values of distance? Using the D array. For int I equals to 1, I less than equal to n, I plus plus, system.out.println distance of source vertex to the vertex I. So as I told you, I indicates what? The vertex, wherein D of I indicates what? Distance of source to I, isn't it? So source to vertex I is D of. The D of I contains the distance from source to I. So print all the distances, right? And follow that, we have a main method where I create the object of the class DIJKSTRA, call read cost adjacency matrix that reads the graph, and the DIJKSTRA method which will now compute the shortest distance. So remember, you have two arrays, visited and D array. Entries of all visited array should be equal to 0. D array should be infinity, where the D of source should be equal to 0. So repeat the steps, finding the U which is not visited, yes, and having the minimum distance value in D. After finding, mark it as visited and update the distance of all the neighbor vertex of U which are not visited. Later, print the distance. This is what the logic of the program here is. Okay. So if I execute this program onto the compiler, so you will get the output. So I have just pasted the output here. The number of nodes is read as 6. The cost adjacency matrix has been read. The same cost adjacency matrix which I took for the example purpose, and entering the source matrix, source vertex is 1. So it will print the vertex 1 to 1 is 0. Obviously, source to source is 0. Distance will be stored as 0. You know that. 1 to 2 is 10. 1 to 3 is 15. 1 to 4 is 22. 1 to 5 is 24. And 1 to 6 is 23. Right? This is the distance of source vertex to your other vertices. Kindly go through the program. Thank you.